So this is Chapter 2, Section 8, Functions and Operations and Composition. So what we're really going to be doing is we're going to be given two functions. We'll call those two functions f and g right now. Remember, when we write f, it's in the context of functions. We really mean f of x. And when we write g in the context of functions, we really mean g of x. So if we're given any two functions, f and g, then for all values of x for which both f and g are defined, that means the intersection of their domains, we have the following. So on the left-hand side is we have the notation that I'm introducing, and then its definition is on the right-hand side. So this is function addition, and we read what's on the left-hand side this way: f plus g of x is equal to f of x plus g of x. Similarly, f minus g of x is equal to f of x minus g of x. And f times g of x, remember when we don't write any symbol, we just write them next to each other, like AB, that's A times B, FG is F times G. F times G of x is equal to f of x times g of x. And the quotient of f and g of x, or we can just say f divided by g of x, is equal to f of x divided by g of x, provided g of x, of course, is not equal to 0. So literally, we've already done this. And believe it or not, you've already seen this in a really simple form. In our last lecture, we talked about adding, given a parent function, f of x, we created a new function, g of x, by a vertical shift, by adding c. But there is always the constant function, m of x is equal to c. That means for every value of x in the domain, every single one of them, the output is c. This is just the graph of a horizontal line. Remember, the function can always be replaced by the variable y in the context of graphing, and y is equal to c is a horizontal line. So I could go back and rewrite this vertical shift as g of x is equal to f of x plus m of x. But f of x plus m of x we can now write as f plus m of x. So you've already actually seen some of what we've been doing. You just didn't realize that's what it was. It was going to take on a life of its own. So let's go ahead and do some of these problems. And just to get you some used to this, we're going to define f of x is equal to x squared plus 1, and g of x is going to be equal to 3x plus 5. So let's take a moment and think about their domain. So the domain of f are all values that all real numbers, so that when I square that real number and add 1 to it, I get a real number. So the domain of f is literally every single real number. There's no restrictions. In the domain of g, this is a linear function, and it's not a vertical line, so the domain of g is also minus infinity to infinity. So if I take their intersection, I just get minus infinity to infinity. So the domain doesn't shrink, it stays the same. The domains will always, when you take the intersection of two sets, the resulting set will always be the same set or a smaller set, in some sense of the word smaller. So for number A, we're actually asked to compute f plus g evaluated at 1. So there's two ways to do this. Well, by definition, it's f of 1 plus g of 1. That's by definition. So f of 1 is 1 squared plus 1, and g of 1 is 3 times 1 plus 5. Well, that's just equal to 1 squared is 1, so 1 plus 1 is 2 plus 3 plus 5. So that's equal to 10. But if you want, you can actually do it another way. And I'm doing it this other way because some of you might be curious. Is that the same as just adding x squared plus 1 plus 3x plus 5? Well, I'm going to get x squared, writing in descending powers, plus 3x plus 6. Just collecting like terms, and really our only two like terms are the 1 and the 5. So let's evaluate. Let's just suppose that f plus g is equal to x squared plus 3x plus 6. So there's an x there. There's, f of g of x. So I'm not going to try to write it or bother to erase, but just recall there should be a little b, f plus g of x is equal to. So let's do f plus g of 1. So that means I'm just going to plug in 1 in all of this. That's plus 6 there. Make the correction. Times 1 plus 6. Well, that's equal to 1 plus 3 plus 6, which is equal to 10. And I get the exact same answer. So you can do it either way. You can actually combine the two functions, add the two functions together, and compute it, or you can just do it this way. Just compute f of 1 and g of 1. I'm going to suggest that you do it this way, because sometimes we won't be able to easily add functions together. And this follows immediately from the definition. But I remember having that question when I was first introduced to these types of functions. So now let's do f minus g of 3. And by definition, that's the same as f of 3 minus g of 3. Well, f of 3, right here's our f function, is 3 squared plus 1. And here you must be very careful. Since g of x contains more than one term, you absolutely must write parentheses in. And then you evaluate 3 times 1 plus 5. And now it's just really just a piece of cake. 3 squared plus 1 is 9 plus 1. Minus in parentheses. 3 plus 5 is 8. So, okay, now I'm not doing what I'm supposed to do. I'm doing f minus g of 3. We'll actually go back and do f minus g of minus 3 in just a second. So that gives me 10 minus 8, which gives me 2. Now the problem literally asks us to do a different one, and it's not going to hurt. Let's do f minus g of minus 3 this time. And I actually challenge you to pause the video and do it on your own. That's going to be f of minus 3 minus g of minus 3. So that's going to be minus 3 squared plus 1 minus, I'm going to write my parentheses here, 3 times minus 3 plus 5. So let's go ahead and just simplify. Minus 3 squared is 9, and I'm going to add 1 to it. And then I'm going to subtract. 3 times minus 3 is minus 9 plus 5. That gives me 10 minus, what do I have in parentheses? Minus 9 plus 5 is minus 4. So the end result is 10 plus 4, which is equal to 14. And my next one is C, 1C. We're going to F times G of 5. So remember, that's just F of 5 times G of 5. We will also want to use parentheses there, but it's really going to be natural. So that's going to be 5 squared plus 1 times 3 times 5 plus 5. Well, 5 squared is 25 plus 1. That's 26. And 3 times 5 is 15 plus 5 is 20. And 26 times 20, once you do it, you will get the answer of 520. And over here, we have to be careful because we cannot have G of our input value x be equal to 0. That would result in division by 0. So we're going to have to be careful. Whenever we have division in mathematics, you have to make that check. So that said, let's do number D. So I have F divided by G of 0. Well, that's equal to F of 0, G of 0. Now, looking at G, you already know that G of 0 is not 0, so we're good to go. So that's 0 squared plus 1, 3 times 0 plus 5, and that's equal to 1/5. I'm going to quit Teams. I thought I'd quit everything that might make noise while I'm recording. Apparently I didn't get everything. So here's composition of functions. No, this isn't. Determining domains using operations on functions. Okay, that's where we are. So I kind of already did this. So let's go ahead and look, and let's determine the domain of these, all three of these. So for A, B, C, and D, the domain is always the intersection of the domain of F and G. So once I define the intersection of the domain of F and G, the domain will always be the same for A, B, and C. When I get to G, I'm dividing. So I have to find the element that makes G of X equal to 0 and restrict it. So basically what I'm saying here is I'm automatically going to find the domain of A, B, and C, and D. A, B, and C will be found completely when I find the domain of A. When I go to find the additional criteria for D, I have to check to make sure G of X is not 0. So let's go ahead and let's think about the domains. So F of X is equal to 8x minus 9. Recall that's the same as Y is equal to 8x minus 9. Why? Because F of X is equal to Y. So this is a line with a slope 8, and it's not a vertical line. So the domain of f is minus infinity to infinity. So what about g? Well, g of x is equal to the square root of 2x minus 1. And I know we know about complex numbers, but these are all called real valued functions. That's the assumption for this class. And you would never encounter a complex valued function unless you were going into some discipline where there was an awful lot of math. And of course that's going to be if you were a math major, but it would also be perhaps if you were going into electrical engineering. So we cannot have what's underneath the radical sign less than 0. So we go over here to the side and we solve the equation 2x minus 1 is less than 0. So that means 2x is less than 1. So that means x is less than 1/2. So that tells you the area of the domain that has to be restricted. So the domain starts at 1/2 is okay. That may not be the best way to go. So this is the area of undefined, but elements x values excluded. Well, really what we want is x values included. You can get it. So really we want 2x minus 1 to be greater than or equal to 0. And this will give me included values. So solving that, we get x is greater than or equal to 1/2. And this is probably easier to deal with because these are elements in our domain. I'm so used to doing operations on sets that going from excluded to included is just a piece of cake, but you all are new at this. So the domain of G is 1/2 is included, and it goes all the way to infinity. So we have to take the intersection of these two sets. And when one of the sets is the real numbers, the intersection is always the smaller of the two sets. So the intersection, it's denoted this way, minus infinity to infinity. Take the intersection with that and 1/2 and infinity. And we're going to get 1/2 to infinity. But again, let's remember one other way we could have done this. When in doubt, we write two number lines, right? And the top number line represents minus infinity to infinity, and the bottom number line represents 1/2 to infinity. So there is my 1/2, and I'm going to write in what's included. 1/2 is included in it, and everything above it, which I'm just going to do by scribbling this red line. Over here, everything's included. Minus 1/2 to 1/2, everything is included. So when we take the intersection of the two, we only take the portion of the number line where both the top and the bottom are shaded. So since minus 1/2 is included in the shaded part, and then everything on to infinity, by taking the intersection, Remember, the symbol for intersection is this. We get the exact same result. So I just found the domain for A and B and C. So now what we want to do is find the domain of D. Is it going to be any different? So back to where we were. So the domain of D is going to basically be the same domain that we figured, except we have to exclude any value of x in that existing domain, which recall was 1/2 included to infinity. We have to exclude anything in this set right here that makes g of x equal to 0. So how do we know when g of x is equal to 0? Well, we set g of x equal to 0 and solve for x. So if I square both sides, square 0, and I square 0, 0 times 0 is 0. So that gives me 0 is equal to 2x minus 1. Solving for x gives me x is equal to 1/2. So that means I have to exclude 1/2 from this domain. Well, it's actually in the domain because of the closed bracket. So I just simply rewrite my domain, excluding it, and the domain is 1/2 to infinity. So this is an open interval, and it's open on the left-hand side, which means 1/2 is not included on the set. When you have the square bracket, it means it is included. So we already figured out the domains of the above functions by actually figuring out the answer. So here's the difference quotient. This is one of the best insights of calculus, and it's an insight that Isaac Newton and his contemporaries who invented the calculus discovered. And it has its own name on its own, and it's called the difference quotient. So we talked about this when we were talking about the average distance between 2 points. So let me see if I can draw just a little bit bigger what they want you to see. I have no doubt I can draw it. My only problem is getting a nice curve using my tools. This is pretty sparse on tools, but the upside of it being sparse on a lot of drawing tools is that it loads fast, it doesn't crash very often, and it's easy to use. So let's draw, I'm just going to try to draw, what is this thing right here? Nope. Let's not play around. Let me just try to draw this freehand. So what I'm going to do is draw a curve. So it's not the best curve in the world. As a matter of fact, I don't even like it. I want it to be a little bit more curved. So I can try to draw a parabola. So I want to know the average rate of change between this point and this point. So remember, I can label this as x2, y2, and this is going to be x1, y1, and when we draw a line through it, those 2 points, we actually get what we call the average rate of change. That's going to be what's guiding us for the difference quotient. Except what we're going to be doing is this is the average rate of change that we can consider the slope of the line to be the average rate of change between the points I'll label this point P1 and P2. But what happens if I get the points closer and closer to each other? What would be the average rate of change if I put another point down here? And of course you would draw a line through the 2 points. And close, as we get the points closer and closer, then the slope of the line gets really, really close to what we say is the tangent of the curve at that point. So a tangent line is kind of, to a curve, kind of tells you what the curve is doing at that point. And that's really, really big in calculus, and it's called taking the derivative of a function. And this curve would be labeled f of x. And when it's a polynomial, it's no problem at all. And you want to find, well, what is the instantaneous rate of change, or the tangent, at this point right here, which I guess I can label x3, y3. And you have a formula to do it if it's polynomials. It's called taking the derivative, but the derivative itself actually comes from looking at the difference quotient. So remember, our difference average rate of change was the change in y over the change in x, and that's equivalent to the slope. So we're going to let P, down here is P, and here's Q, and there's my curve. Let's make this better. This is probably readable. So here's my point P, and here's my point Q. So this has a value of x, f of x. You can call this x1. And this has the value of, I'm going to move out from x h units. So this is the value of x plus h and f of x plus h. So that's what we're defining as the difference quotient. So the difference quotient is just the difference in the y values over the difference of the x values. So the y value is f of x plus h minus f of x, so that gives us our numerator, and x plus h divided by x, and that gives us our denominator. And when I simplify these two, I get that our difference quotient is given by the following formula: f of x plus h minus f of x divided by h. Because after all, h right here is our change in x value. So it shouldn't surprise you that our change in x value, which is h, and is what delta x means, and it tells you right there that that change is h units. So let's find the different quotient of a specific value. So where we get me here? I would give anything if I had graphing tools like AutoCAD support, but then it gets really slow and bulky and crashy. So I'm going to stick with just this instead of trying to move over to Windows, where I do have AutoCAD installed. This is a dual boot machine. Of course, it comes installed with Windows. And I just create another partition and put Linux in it, and hardly ever boot into Windows. So delta x is actually going to be the same as h. Delta x is our change in x values. So now it's just it's a matter of computing f of x. We have to have our function f of x. Sorry, I got interrupted again. This time it's just the telephone. I closed the door and turned off the ringers. So let's go ahead and calculate the difference quotient. So remember, delta x is equal to h, and our function is 2x squared minus 3x. So what I have to calculate is f of x plus h. So remember, the x plus h is my input value, so I just take 2x squared, and the input is x plus h. And I'm going to square it. And then here it's really a very important idea that you put parentheses here. And then it's just f of x. I'm not ready to do f of x because I haven't got all of f of x plus h in there. There we go. And now we want to put our parentheses in there because we're subtracting more than a single term, and that's going to be 2x squared minus 3x over h. So let's go ahead and simplify. So what we will use is our knowledge of some formulas for squaring. So x plus h squared is x squared plus 2xh plus h squared minus 3 times x plus h minus, in parentheses, 2x squared minus 3x, and all of this is going to be over h. So let's go ahead and simplify that numerator. So what I have to do now is just multiply out. So that's 2x squared plus 4xh plus 2h squared minus, and we're doing distribution, 3x minus 3h minus, I'm going to go ahead and distribute this negative sign, minus 2x squared minus a minus is a plus. That's where the error will occur so many times. Not as so much in college algebra, but more than I like. And all of this is over h. Now we're going to go ahead and take one more step, kind of breaking this down into several. And I'm going to collect like terms. So you just start on this side and you start with the x squared terms. When I've got one written down, and there's the other x squared term, I write a line through it so I know I've got them all, I don't forget them. So there are no other x squared terms. So the next term is the plus 4xh. Are there any other xh terms? No, that's the only one. And then we just go in turn. 2h squared. Are there any h squared terms? Nope. Then we'll do minus 3x. Are there any other 3x terms? There is. There's a plus 3x. And then finally, I'm going to subtract minus 3h. Now, I'm getting much closer. This is going to be equal to, we're going to go ahead and cancel out, 2x squared, those are going to cancel out. So I'm going to go ahead and write this down here. So I'm going to have, and minus 3x plus 3x are going to cancel. So I'm going to have 4xh plus 2h squared minus 3h over h. And now what I'm going to do is bring it over here. And I want to pull out the greatest common factor. And here every term has a factor of an h. So I'm going to pull out an h. 4x times h divided by h is 4x. plus 2h squared divided by h is 2h, and minus 3h divided by h is minus 3. And it's all divided by h. So now I have an h and an h in the numerator and an h in the denominator. So my final answer is going to be 4x plus 2h, sorry, not plus, minus 3. Now that's as far as you go. That is the difference quotient. That is your answer. But for those of you who are going into calculus, I want you to think about something. If our points get closer and closer, then the value of h approaches 0. So as our points get closer and closer, as my point P gets closer to Q, the distance between them, which is h, gets closer and closer to 0. So as h gets closer and closer to 0, no matter what the coefficient is here, I'm multiplying something that is really, really small and getting closer to 0 times something else, so it shrinks it by what we said in our last lecture. So as h goes to 0, the 2h term gets closer and closer to 0, so the approximate answer is 4x minus 3. And indeed, later on you will talk about something that's called a limit, and we'll say the limit as h approaches 0 of 4x plus 2h minus 3 is equal to 4x minus 3. And that's actually the line that is tangent to the point x. So you can literally find the tangent line for any point on that graph. But of course that's not anything we have to worry about in our class. That's the whole point of getting and introducing you to the distance difference quotient. Now here comes the big one. It's the composition of functions. So what we're going to do is we're going to let the input of one function be the output of another function. So the input, the x value of one function, is going to be the output of another function. So let's suppose we have two functions f and g, where the range of g, that's the output set, the range of g is entirely contained in the domain of f. So that's the important clause right there. So when you say entirely contained in the domain of f, they can be the same set, or f can be a smaller set than g, but it's still contained in the set. Then when we input a value of x into the function g, we get an output value, which we denote by g of x. So that's a real number. What can I do with that real number? Oh, by definition, or by stipulation rather, that output number has to be in the domain of f. And hence we can use the value of g of x as an input to the function f, and denote it as f of g of x. So this is pronounced f of g of x, or x composed of g of x. To formally define these concepts, we have the following. So this is an important formal definition. This is really the first place in this course where you have to answer questions. You have to use this formal definition. Let f and g be two functions where the range of g is contained in the domain of f. Then f composed of g of x is this, f evaluated at g of x, where the notation f composed of g of x is called the composition of f with g, or f composed with g. The domain, and here's the definition, of f composed with g of x are all elements in the domain of g such that g of x is in the domain of f. So the domain, when we try to find the domain of a composition of functions, then it's either going to be the domain of g itself or a smaller set. So that's where we look. So let's first just do some stuff using compositions of functions. Compositions of functions are really important in mathematics. So it's not just something that we dream up to torment you with. It literally is used all the time. Composition of functions. So f of x is given to be 2x minus 1, and my g of x is equal to 4 over x minus 1. So we're just going to do what it asks us to do at this point, and then we're going to ask about what is the domain of f composed of g, and what is the domain of g composed of f. So remember, by definition, f, and that's a circle, not a dot, but a circle with, an actual hole in it. F composed of g, looks like fog, I know, of x, is by definition f evaluated at g of x. So they want us to find f composed of g of 2. So that's the function f evaluated at g of 2. So the way I do it is I find g of 2 first, and that's 4 over 2 minus 1, which is 4 over 1, which is 4. So then I just rewrite f evaluated at g of 2 is f of 4. But f of 4 is 2 times 4 minus 1, which is 8 minus 1, which is 7. So now let's do g composed of f. Do you think they'll be the same answers? All I've done is just switch the values, switch the places rather of f and g. So 5b. So let's compute g composed of f at minus 3. So you come over here, and you know this is just g evaluated at the value given by f of minus 3. So we have to find out what value is f of minus 3. Well, f of minus 3 is 2 times minus 3 minus 1, which is minus 6 minus 1, which is equal to minus 7. So I'm good with that. So now I know that f of minus 3 is minus 7. I compute g of minus 7. Well, that's 4 divided by 7 minus 1, which is 4 divided by, that's minus 7 minus 1. 4 divided by minus 8, which is equal to minus 1/2. Okay, not so bad, right? Really not so bad. So the only difficult thing is finding the composition of functions and its domain. So all that I care about here, well, we're going to go ahead and do it, but really the only thing I care about here is that you find its domain. I'm going to show you one particular way you could do this, but I don't really think it's helpful. So let's go back up here. So apparently Tuesday afternoon is not a good day to do videos, but I want to get these out. So we were asking, we have f composed of g of x, and we want to find its domain. And actually we want to also find the domain of g composed of x. So that means I need information about both of these functions. So I need to know the domain of x, of f. Well, that means the square root of x has to be, let me write this better. It means the square root of x has to be greater than or equal to 0. Squaring both sides, that means x has to be greater than or equal to 0, because these are real valued functions. So the domain of f is 0 to infinity. And the range of the square root function, remember, these are real valued numbers, and they're always 0 or positive. The range of f is also 0 to infinity. We're going to use both of this information. We have to ask the same question over here. Sometimes we don't have to answer all of these questions, but the question asks us to find the domain of f composed of g and the domain of g composed of f. So the domain of, this is just a linear function with slope 4 and y-intercept 0, 2. So the domain is minus infinity to infinity, and the range is also minus infinity to infinity. So now is when we have to have the definition. So the domain of f composed of g is all elements in the, here's the important part, domain of g such that g of x is in the domain of f. That's of f. Maybe I'll put that as f of x there. That makes it look more like a function. So what that tells us is that the domain I'm going to find is going to be taken from this domain. It's either going to be the same or a smaller set. So it's all elements in the domain of g, so that's a big huge domain, minus infinity to infinity, such that g of x is in the domain of f of x. And that's the key point right there. G of x is what? G of x is 4x plus 2. And I need 4x plus 2 to be in the domain of f. I'll put x there if you want that. So I need 4x plus 2 to be greater than or equal to 0. So we just go ahead and we solve. 4x is greater than or equal to minus 2. So x is greater than or equal to minus 2 divided by 4, which is equal to minus 1/4. So if, not 1/4, minus 1/2. There we go. So x greater than or equal to minus 1/2. If x is greater than or equal to minus 1/2, then f of x, then g of x is in the domain of f of x. So the domain of f composed with g is given by this. Okay. So now I'm going to erase, because I want to keep this information up here. So if you need to scribble all this down, press pause, whatever you need to do. I'm going to make my erase area really big. Something really satisfying about watching that erasing function. So now we're going to ask the question, what is the domain of G composed of F? So you need to know what it is. The domain of G composed of F is all elements. Where are we taking them? In the domain of what function? Of F. If it were the same, I wouldn't have erased it. Such that f of x is in the domain of G. So that's the reason I kind of like writing just f for the function name and using the symbol f of x to mean an element in the range. So the domain of f is 0 to infinity. So the resulting domain cannot be any bigger than 0 to infinity. So that's the important part. We start with looking at the domain of f, and then we're going to carve out some x values, or maybe not. Maybe we can use every x value in there. So f of x, which is the square root of x, has to be in the domain of G. Well, the domain of G is minus infinity to infinity. And the square root of x is always in the domain of G, no matter what. So I don't have to have anything to worry about. So I just take the intersection. It's just all values in minus infinity and infinity that are contained in 0 to infinity. So this is the range. This is the f of x values, which stand for the range. And this is the domain of G. And this is the domain of f. So what do? I take my old intersection. And if I take the intersection of minus infinity, infinity with some other set, then that other set is different from minus infinity to infinity, you get that set. Okay. Now, they actually wanted me to do one other thing, and since it could be on, it won't be on your exam, I think it's a waste of time myself. They want you to determine the composite function. So f composed of g of x is equal to f of g of x. Well, what is my f value? It's the square root. And what am I square rooting? I'm square rooting g of x. So I write underneath here 4x plus 2. But that's not where you want to get your domain necessarily, because remember, you're taking domain elements out of g. So coming over here, I don't know any easier way to find the domain other than what I just did. And that's how the book does it too. And they want to find, well, can you give me what g composed of f of x is? Well, by definition, that's g. Its input value is f of x. And g is given by 4 f of x plus 2. But because why? My x is f of x. So my f of x is the square root of x plus 2. So it's equal to 4 root x plus 2. And anything else? Okay. Showing that f composed of g need not be the same as g composed of f. We actually did this already. I showed an example. In our very first example we did, I showed that f composed of x is not the same as g composed of x. And we can do it here, but I'm kind of over this. I want to go to the mathematical reasoning. And here it is. Let f be the identity function, and let g be any real valued function. All of our functions in this context are real valued. What is f composed of g of x? What about g composed of x? Does your discovery violate what we discovered in example 8? So just so you know, and let it be forever written, that in another example, not example 8, it is the following is a theorem. F composed of g of x is not necessarily the same as g composed of f of x. Okay, I think I've got to the very end without any further interruptions, and I think this is the very last section in chapter 2, and it is.